Hello, everybody. Welcome to EEE 146 Power Electronics, Chapter 2, Power Computations, Part 1. So today we're going to talk about mainly power and energy, because that's part of the power electronic circuits. We always want to measure how much power we're getting, how much energy is flowing, and it's very critical to any type of converter. So we got to go with definitions first. First, we got to talk about what instantaneous power is. Basically, any time a circuit is running, you could freeze time and take a snapshot, and how much power will flow into the circuit. That's your instantaneous power. Right? You can calculate instantaneous power by the voltage and the current at that exact second. Right? Even if the waveform is moving, you calculate the 1 point on the sine wave or square wave, multiply by the current at that point, and those two is your instantaneous power. Okay. Now we have this passive sign conventions we always have to look at. Is power can be either going into a device or coming out of device, right? And that's the difference between what a load is versus a source. A load takes power and energy out the circuit. A source puts power and energy into the circuit. So if we have the current flowing into the positive terminal of a device, right? This figure A. Both of these numbers are positive, so positive V and a positive I, and then you'll get a positive instantaneous power, and that's a load, because your positive power means you're absorbing power and energy from the circuit. You're taking it out of the circuit, like a resistor, okay? Now, if current is leaving the source, you see how the arrow is pointing outwards now? This current is now negative. So if you multiply a positive voltage times a negative current, because current is flowing out, you can get a negative instantaneous power, and that means a power supply, meaning it's a battery, a generator, or some device that's pushing current into the circuit and supplying power. Okay? So the way I like to think about it is always look at the positive terminals. Current always flows into loads because then the energy gets popped out of the circuit. Sources always put current into the sources put current into the circuit to put energy into it and power so we can run things. Okay? So how can we determine the power direction from sources itself? Because sometimes, you've probably seen in Engineering 17 or 117, a voltage source can be a power or a load, depending on what it is, right? A battery is technically a voltage source, but you could be pushing energy into the battery to charge it. So how do a resistor is pretty obvious, right? Resistors can't put energy in, so it's only one way you could take energy out. But the easiest way to look at it is look at a source. If the current is flowing into the positive terminal, it's absorbing power. So this could be a battery getting charged. Okay? If the current is flowing out of the positive terminal of the voltage source, then it is a supply. So power supply, a battery again could be a power supply if it's discharging into the circuit. Okay. So the easiest way is just check which way the current is flowing. But you have to keep track of the positive orientation of the voltage source, right? So always reference this as a positive terminal right here of the voltage source. Okay. And every voltage source have to tell you what the positive terminal is. If you have a voltage source, you don't know which one is positive or negative, you literally can't do anything with it. Okay. So that's instantaneous power. From there, we can start talking about basic physics of energy and power. Okay. So energy, or other words, we call it work. They're the same thing, right? This is a total amount of, they say the energy being put into the circuit or the amount of work being done by the circuit. For example, you have an electric fan. Electric fan will push air through. That's work being done. You're moving air molecules, okay? It takes energy to run a fan to do work to push air through your house, okay? How can we define energy in terms of electrical quantities? Because we're electrical engineering, that's what we care about the most. Is the total energy used in a given time frame. So we have to say from now to maybe 10 minutes from now. So maybe like a 10-minute interval, maybe a 5-second interval. There's some time frame we look at. How much energy do we use within that time frame? That's what total energy means. So anytime we say within a time frame, you have to see, 1 hour here, 0 hours there. You take the difference. That's basically integral, right? Integral scare people. All integral is taking one end, subtract from another end, and averaging, maybe, or adding them all up, okay? So integral over 0 to t, where t is whatever you choose. So the time we're counting on a stopwatch, add up the instantaneous power. So every millisecond that goes by, every second that goes by, start adding up how much instantaneous power is happening, and that's your total work. Now remember, instantaneous power is a rate of energy transfer. Okay, if this is a big number, we're going to be pulling a lot of energy through the circuit. If it's a very small number, we're pulling little. If this is 0, we're doing nothing. The circuit's turned off. Okay. And the units for energy is always going to be either joules, if you're more in the scientific level, or in power engineering, we typically go by kilowatt hours. You ever look at a utility bill, you're usually charged to your house, it's charged by kilowatt hours, not joules, but they are interchangeable. Joule is just an SI unit the whole world knows. Kilowatt hours is more specific to power engineering and electrical engineering, okay? So work is always the integral of the time we count, and then just add up instantaneous power. And that's your total energy use. Now, another way to look at this also is what is the power of the circuit. A lot of people use power and energy interchangeable, and they're actually different. Power is an average of energy flow in a given time period. That's why it's called average power. Okay, so if we flow 10,000 joules over 5 seconds, you can find the average of 10,000 divided by 5 seconds, and that's your rate power, or the rate of energy transfer. Okay, so how do we calculate the power? Well, it's very simple. You take the total amount of energy used and divide by the time we counted. So right here, you see is the total energy divided by the time. So if I took a stopwatch and watched the circuit for 1 minute, that T is 1 minute. If I did it for a 24-hour period, it's 24 hours. Or maybe I have a power bill. Look at your monthly power bill from utility. They calculate the average power used, and their T is 30 days, because that's a standard month. Okay, so it's always energy divided by the time you count, you get your average power. Now we could do it more mathematically and say, well, energy is always the integral between 0 and the time you count, and then you add up instantaneous power every second through it. But this time you divide by the total time, because we're taking average. Average always means count up between a period, between a window, and divide by that many times you count it. Okay, so if we count for 24 hours here, we divide by 24 hours. Okay, so average power over time. So these two, very important to understand: energy and power. Right? Very simplified formula is average power P is equal to the energy divided by the time duration that we look at. Okay. So, easiest way to look at this, kind of let's see the simple circuit, and we'll see the output here where we have a voltage that is on at 20 volts and then turns off at 10 milliseconds, and then it's off until 20 milliseconds and it turns on. So this voltage is intermittent. It's turned on for half the time and then it turns off. So it's on, off, on, off, on, off. Okay. I put this T right here because this is a period where it repeats itself. And you can see up here, they mathematically showed it with 20 volts between 0 to 10 milliseconds, and 0 between 10 milliseconds and 20 milliseconds, and then it just repeats itself over and over again. Okay. Current is going to be 20 amps between 0 and 6 milliseconds, and then it'll be negative 15 amps between 6 milliseconds and 20 milliseconds. Okay, so we have current flowing in positive direction, and then it reverses over to negative direction, and then it repeats itself over and over again. Okay, so if I have a voltage and a current, notice is V of t, I of t, in my circuit, can I figure out my instantaneous power at every second or every millisecond? Yes, you can. Right? Graphically, we just look at the two numbers and we just multiply them together, because remember, P of t is always equal to V times I. Okay. The way I like to do this is look at two graphs, see where the second any of these graphs changes, put a barrier and say, let's calculate. So between here, all the way to about 6 milliseconds, both the voltage and current are 20 volts and 20 amps respectively. So nothing's changed here. So down here, I would write between 0 and 6 milliseconds, I know I multiplied 20 by 20, 20 volts times 20 amps. My total instantaneous power is 400 watts. Remember, power is in watts. Okay. And so I draw my graph and say instantaneous power is this much. We're up until 6 milliseconds. At 6 milliseconds, the current flips over to negative 15, so we have to recalculate it. So we still have 20 volts up here, but we have negative 15 amps here. So 20 into negative 15 is negative 300. All right. So here you're going to get, actually, I see this quick little error right here. My apologies. I wrote negative 6. It's actually negative 15. Okay. So 1, 5, 1, 5. Okay. Sorry about that. All right. So right here, between 6 and 10 milliseconds, because that's 10 milliseconds where something changes, we have 20 volts times the negative 15 amps, which is negative 300 watts. So right here's negative 300. Now remember, at 10 milliseconds, the voltage goes away. So you see the graph changed, so we have to recalculate. So at 10 milliseconds, even though we have negative 15 amps, we got 0 volts. So I know 0 times negative 15 is 0, so nothing happens. So we're flat 0. And then it repeats itself over and over again. Because the waveform repeats, and we just repeat it over here. So you see instantaneous power can change drastically based on only one of the two graphs. If either voltage or current changes, power changes drastically one or the other. The thing is, if we just started at 20 volts right here and only looked at the voltage, we would never thought that we'd have negative power, right? Because we don't see any negative voltage here, so we assume it's positive all the time. That's incorrect. Look at the current. The current is positive and negative as well, so that can really complicate things. So instantaneous power can get very wonky waveform-wise, depending on how complicated your voltage and current is going to be. So it's very helpful to be very meticulous when you're calculating this. Simple errors can arise very quickly, and then it kind of blows up your problem. Okay. So we have instantaneous power as a graph here. We can now talk about calculating total work done and the energy of the circuit and the power of the circuit. So first, let's talk about total work done. And let's calculate it in joules. Now notice I have 3 different phases of this waveform up until it repeats itself, because instantaneous power is different for all 3 of these points. Remember, total energy is counting from 0 to the end where it repeats itself, in this case 20 milliseconds. Okay, so we're going to add up instantaneous power across this whole area. But the thing is, it's cut into 3 pieces. We have 400 watts between 0 and 6. We get negative 300 between 6 and 10. And then we get 0 between 10 and 20. So we need to actually split this up into 3 integrals. Because remember, integrals, you can always add them together and split them up with addition. Not multiplication, but addition and subtraction, you can always split them up. So what we'll do is between 0 and 6, we'll have another integral between 0 and 6 milliseconds right here. And we're going to say, well, it's 400 watts. Instantaneous power is 400 watts. So that covers this first block. The second block, we have to do a separate integral between 6 and 10 milliseconds, except we're going to have negative 300 watts here. And the last one, we technically should go between 10 and 20, but it's going to be 0, so I just wrote 0 because nothing's going to happen. Right? You're adding up a bunch of zeros, so it's obviously going to be 0. So with this integral, remember, you always take the larger number of the top number, subtract by the bottom number to see the distance we integrate. So this is going to be 6 minus 0, so we integrate for 6 milliseconds. And then we multiply by the number inside, which is 400 watts. So it's going to be 6 milliseconds times 400 watts. We're then going to add a second integral right here, and this is going to be between 10 and 6. So you get 10 minus 6, which is 4 milliseconds. You multiply by negative 300 watts. So you can see the second one is actually working against us, which makes sense because it's negative power. So at the end of the day, for the first area right here, we're sending power, sending power into the circuit, right? Or rather, the device is using power or energy, sorry. Between 6 milliseconds, energy is negative, so then we're putting it back in the circuit. So this device is absorbing some, putting some back in. It's a little back and forth operation. So we can add the total energy of the whole time used, which is 6 times 400 plus a negative 300 times 4. So we're going to net out a difference of 1.2 joules. So this whole circuit with this push and pull of energy, we netted out 1.2 joules into the load or into the device. Okay, that's the net gain. Now, with the total energy, we can also figure out the power, right? Power is always work over time. Well, we know work, we did 1.2 joules worth of work. How long did it take us to do that amount of work? Well, we did it within 20 milliseconds. So you take 1.2 joules divided by 20 milliseconds, we end up getting 60 watts. Okay. In terms of wattage, what does 60 watts mean to you? That's similar to your laptop charger. Your laptop charger probably runs between 40 and maybe 30 and 60 watts, maybe 100 if you have a huge gaming laptop or something. But 60 watts is a good average for a laptop charger. Okay. Old incandescent light bulbs run about 60 watts. Your phone charger is probably running about 20 watts, just to give you an idea. Right. Okay. But this is nothing compared to like a microwave. A microwave runs at like 1,000 or 1,500 watts. So just in terms of appliances, that's kind of giving an idea of what does 60 watts mean to you. Okay. So even though 1.2 joules isn't that much, we did it so in a very short window. 20 milliseconds, very, very tiny. So we end up getting a pretty sizable amount of power out of this circuit. Okay. So that's how you calculate energy and power in any circuit. Okay. Here, we're going to take a 15-minute break where I want you to work on this exercise. I have voltage and current waveforms. I want you to do exactly what you did before. I want you to calculate instantaneous power, POT, for each segment where it changes. And then I want you to calculate the total work done in joules for the whole circuit. And then I want you to calculate the average power of the voltage and current waveforms at the end. Okay? So notice the voltage is 40 volts, and then it flips to negative 40 back to positive and negative. So it's kind of like a square wave where it does it every 10 milliseconds. Okay. And then it stops right here. So this whole graph is one period from 0 to 40. Okay. The reason why it's at 40 is if you look at the current waveform, it's not symmetrical. It changes quite a bit. Current goes from 0 to 10. It's 0 amps from 0 to 10. From 10 to 20 is positive 5 amps. And then from 20 to 35, not 30, 35 is negative 10 amps. Okay. So within this area, you need to go piecemeal one by one, figure out your total instantaneous power, figure out your energy, figure out your average power, and then we'll come back and we'll check your answers. Okay. So see you back in 15 minutes, and good luck. All right, hello, welcome back to our exercise for the energy and power that we're talking about. So we said, hey, there's some voltage and current waveforms, so let's start calculating some power. So let's see how we do it. First thing I can do is look at the waveforms and kind of partition where things changes so we know what areas we need to look at and integrate. So here we have a total of 5 places we're going to look at. From 0 to 10 milliseconds, everything's steady. So we're going to have this red partition right here. From 0 to 10 milliseconds, instantaneous power is going to be equal to your voltage of 40 volts times your current of 0 amps. So we're actually at 0 watts. So nothing happens between 0 and 10 milliseconds. And at 10 milliseconds, our voltage switches over to negative 40 and our current turns on at 5 amps. So from 10 to 20 milliseconds, we're going to have to calculate instantaneous power here, the light blue. So from 10 to 20, instantaneous power, P of T, is equal to negative 40 volts times 5 amps. So we're going to have negative 200 watts for this middle area here. All right. And then at 20 milliseconds up until 30 milliseconds, the voltage snaps back to 40 volts and the current flips to negative 10 amps. So for green, from 20 to 30 milliseconds, instantaneous power is 40 volts times negative 10 amps. So we can get a negative 400 watts. And then from 30 to 35 milliseconds, the voltage will swap over to negative 40 volts. From 30 to 35, instantaneous power is equal to negative 40 times negative 10 or positive 400 watts, because you have two negative and the negative multiplied together is a positive. And lastly, from 35 to 40, we're going to have instantaneous power be a negative 40 volts right here, but then 0 amps, so we can get 0 watts coming out. So realistically, only the middle 3 bands actually had instantaneous power. On the outer 2, it was turned off because the current wasn't flowing to begin with. Okay, so that's the instantaneous power per segment. We can now look into calculating the energy for the whole circuit. So the total work done, again, remember 5 spots. So I kind of just reminded myself from 0 to 10 milliseconds, it's 0 watts. So we're just going to add up each segment together. So we did 10 watts or 10 instantaneous power of 10 times, or 0 times 10 milliseconds, so 10 minus 0, but that's out to 0 anyway because nothing's flowing. So for the blue area, we got negative 200 watts. So negative 200 watts from a distance of 20 milliseconds minus 10 milliseconds. So the total length is 10, 20 minus 10. So, and that's in milliseconds. The third one right here in green is going to be negative 400 watts over another 10 millisecond window, which is 30 minus 20. And then the last one, or second last one to look at, is this purple one. We're going to have positive 400 watts right here. And our window is going to be from 30 to 35. So we're going to have 35 minus 30. So it's only a 5 millisecond window. And the last one is another 5 millisecond window from 40 to 35, but it's going to be 0 watts. So 0 watts times 40 minus 35 is pretty much 0. So calculator comes out, multiply these all together. You're going to get 0 for the first one, negative 2 watts for the second one, negative 4 watts for the third one, and then positive 2 watts for the fourth one, and 0 for the fifth one. Add them all together, our net total is negative 4 joules. Okay, so even though the waveform's going up and down, just the way the current turned on in particular areas, we ended up actually putting a lot of energy back into the system. So this circuit where we are measuring our voltage and power, our current, we're actually putting 4 joules back in this system. So it's negative 4 joules. So this is like a source right now. Okay. So with the power total work done, we can now figure out average power. Capital P is equal to work divided by time. So we have negative 4 joules worth of work, and the total time our circuit was on was within 0 and 40 milliseconds. So our net time is 40 milliseconds. You divide these two out, and you get negative 100 watts. So for a short time the circuit was turned on, the average power was actually pushing 100 watts back into the circuit. So we're a 100-watt source. Okay. So just wanted to give you an exercise, show you how the math is done, a little different from the example I showed you. Okay. So moving on, the other thing we need to talk about is inductors and capacitors. We're going to use them extensively in power electronics. All electrical engineering uses inductors, and we're really capacitors. Inductors are kind of used, but capacitors are used everywhere. I think you really, really need to know how these operate and work, not just memorize equations, because life gets a lot easier when you're looking at why is this capacitor here, what is it doing into the circuit. So we're going to go down with English, not mathematics, to try to understand what's going on. The math comes after we understand in English what's going on. Okay. So number one thing to know, inductors always resist the change of current and try to keep it steady as much as possible. Okay. The inductor will always act like a sponge and absorb or supply energy into or out of the circuit to resist the change in the current. So the inductor has like a room for energy. If we try to say, hey, I want to push a lot of current through, the inductor's like, nope, I don't like you to change too fast. So instead, I'm going to absorb the energy from the circuit to slow down the current. So instead of changing current quickly, I'm just going to take the energy and we're going to change slowly. I'll eventually let you get to the high current, but I just want to be safe. Let's do it slowly, and I will absorb the extra energy that you want to try to push out. On the opposite side, if I'm full and my inductor has a lot of energy and the source is like, well, I want to lower the current, we need to go down quickly. The inductor is like, nope, I don't like the resistance change in current. So you can say, let's go down, but I'm going to keep the current high, and I'm going to dump my energy out of my circuit or my inductor to try to keep that current high, and we'll slowly let the current flow. I know you wanted to do fast. I wanted to do slow, and I'll supply the energy to make sure we have a slow landing, a slow decrease in current. And that's all inductors do. Okay, it's a tank of energy that can either absorb or supply energy to make sure the current moves slowly. No abrupt changes. We don't want on and off switches. I don't want to go from 10 amps to 100 amps instantly, right? We're going to go from 10 to 11 to 12 to 20 to 30. We're going to do it slowly, and my energy will help keep it slow. Okay. So in terms of circuit analysis, we can kind of look at a very simple circuit. We have a source right here. And let's say we have an inductor. Let's say it doesn't have a lot of energy. And the source all of a sudden says, hey, let's increase the current. Current, let's go up. Inductor's like, nope, not just yet. So Real quick, what happens is this source immediately flips on and says high current. So it's going to push a lot of current out this top branch right here. The inductor is going to literally stop it. So right here in this yellow, you can get a lot of positive charge. So you think of like a lot of pressure on that top rank, the top wire right here. And the inductor is going to say, nope, I'm not going to let you through. Instead, the inductor is going to absorb some of the energy you're trying to push through, and this current is going to be slowly flowing. Okay. Now, because you have a bunch of pressure and a bunch of positive charge here and nothing on the bottom, or very little, then that means there's going to be a huge or a big voltage chain, a big voltage across an inductor. Anywhere you have a bunch of pent up energy up here and not much energy here, that's a voltage difference. Okay, so anytime you're trying to increase the current suddenly, you're going to get a pretty big change in voltage across an inductor. Okay, so this delta V is always going to be positive because it also wants to absorb the energy. So we have all this energy right here. The inductor is just going to absorb it slowly. So our instantaneous power is going to be positive because we're taking energy out of the circuit to charge up the inductor. Now, eventually, the inductor is going to get fully charged, and then it's going to let all the current through. But that could take some time. Okay, so this is what happens when you try to increase the current. Is we got to wait a little bit, get a little pressure here, build up some voltage, and let the inductor slowly absorb the energy and let the current through. Okay. Now, what happens when we have a lot of energy in the inductor right here? So let's say the inductor's been working for a while, we got a lot of energy stored, and all of a sudden I want to decrease the current. Let's say we're running here pretty well, and the source is nope. Let's cut the current in half. From instead of 10 amps, I want 5 amps immediately. What is the inductor going to do? Nope. I don't like the change in current. I'm going to resist it. I know you want me to dump the current. We're going to have less energy flowing through the circuit. I'm not going to let that happen. Instead, I'm going to take the energy I have stored and I'm going to dump it down here to you. I know you want 5 amps flowing from the top. I'm going to give you 10 amps because that's what I want. So when you have a lot of energy down here and not much up here, what do you have? You got the pressure difference again. So all the energy stored down here, not much up here. What happens to the voltage? The voltage actually flips polarity. So this delta V right here, instead of being positive on top and negative on bottom, is going to flip polarity and it's going to be a negative voltage. Okay, current's still going to flow, but now that current's flowing out of the positive terminals because we flipped it, instantaneous power is now less than 0 and it's negative. Okay, so the big thing here is when we're trying to release energy back into the circuit, the inductor is now the source and the current source is technically the load right now. Okay, and that's why the voltage has to flip polarity. Okay, the inductor needs to flip polarity and voltage to be a source. Okay, it's strange, but if you just think in terms of pressure, where's all that positive charge being stored? In this bottom half, if you got a bunch of positive charge and not much over here, how do you label voltage? Voltage will always be a positive where there's a lot of charge, and the negative terminal is when there's not a lot of charge, right? So that's the push and the pull that an inductor tries to do. To kind of sum it up right here, if you have an inductor and you want to increase the current, so in this circuit I say current needs to increase, what is the inductor going to do? The voltage across the inductor will have positive volts. So this will be a positive voltage right here, okay? The energy will also be absorbed by the inductor as well. So when my circuit tells the inductor, hey, let's increase current, inductor says, I will be positive voltage to accept the energy from you until I'm filled up and I'm happy, and then we'll let the current through. Okay. On the opposite side, if I have a lot of current flowing through and my inductor is happy, we're at steady state, and then all of a sudden I said, let's decrease the current. Immediately, the inductor is going to say, all right, I'm going to have negative volts across my terminals. So we're going to flip polarity, negative voltage immediately happens, and then I'm going to start releasing energy to keep the current as steady as possible until I run out of energy, okay? And so that's what happens when the current decreases. Now, the last thing I want to say is what happens when the current's constant? Let's say we're all running and we're all happy, nothing's changing. If there's no current change and the inductor's happy, you're happy, the circuit is running perfectly, there's going to be no voltage across an inductor. An inductor at steady state with constant current is almost like a wire. There is no impedance, there's no voltage drop. It's just a very, very long wire. Okay. It's also going to hold this energy indefinitely until you try to change the current. So if there's no change in current, no voltage across the inductor, no energy changes, so it might as well just be a short circuit at this point. Okay. But whenever you try to change or increase or decrease the current, that's when everything everything happens. Okay. All right, actually, let's spell this. Should decreases. I'm going to change that. Okay. So that's in English what happens with the inductor. Now we got to do some math because we always do circuit analysis. And this is just a rehash of what you did in engineering 17 and 117, all right? But maybe by what we learn now, maybe some of the equation makes more sense, hopefully. Okay. So the stored energy in the inductor is always going to be 1/2 L times I squared. Okay. The way I like to think about this is the more current you push into the inductor, the exponentially faster the energy is going to store. That's why it's I squared. Okay. So I'm going to try to increase the current. If I'm going to make the current go high, we're going to get 2x or x squared, the exponential amount of energy, because the capacitor is going to fill up really fast. Okay. L is here because that's the size of the inductor. The more the wire is wound around the core, the more the magnetic field that can be generated, the bigger the L. So a big L means big energy storage tank. That's the main thing you need to know. Small L means small energy storage. Okay. So in essence of changing the current, the bigger your inductor, the bigger the L, the stronger it is to resist the change in current. So if I'm trying to push 1,000 amps and I have like a 1 microhenry inductor, it doesn't have enough energy storage to stop 1,000 amps flowing, right? It's just not going to do much. Now, if I have a 5 Henry or even a 1 Henry inductor and 100 amps, that 1 Henry is going to stop it for quite a while. Okay, we're going to feel that. So that's all L means, is just how big the energy tank is, how big the inductor is, and how much it will affect your circuit. Okay. So that's energy stored. We're going to use this a lot because a lot of times when you calculate how much energy is stored in an inductor, because we're going to use it later. Okay. You can also figure out the voltage across an inductor by the current. Okay. So very classic equations. Voltage across inductor is L di dt. Okay. Now, remember, L is the size of the inductor. Okay. Now, what does di over dt mean? So I obviously means current. What d over dt means is the rate of change. All you need to know, all this means is if current increases, how fast it increases is going to be a positive number. So if the current is slowly increasing, maybe like 1 amp, 2 amp, 3 amp, 4 amps, the rate of change is going to be a very small number. It's going to be positive, but it's going to be very small. And the way you actually figure out this number is the rise over run. Remember old school Y equals mx plus b? You figure out how much current increased over a time interval. If I went 5 amps over 5 minutes, that's a very small amount of change. But if I went, let's say 1 amp over 1 microsecond, that's an insanely high rate of change, right? And this is going to be a very big number here. Okay. So what this tells me is the faster I try to change the current quicker, my voltage is going to be a lot bigger. Okay, so if I try to do a very fast, if I want to change my current very fast instantaneously at the millisecond level, this is going to be a very big number. We're going to have a huge spike in voltage because you're trying to make the inductor do something really fast. You're going to build up a charge very quickly. Okay. If I say, hey, let's change the current and I'll give you 5 minutes to do it, that's not a big change. So we're not going to get a lot of voltage across an inductor because we're not building that pressure up, because we're letting 5 minutes is a long time for an inductor to build up. Okay. So that's what d over dt means, is how fast. Okay. Now, that's if it increases. What happens if the current decreases? So let's say decreasing current means I'm trying to take energy out the circuit, right? I'm trying to dissipate the energy in the inductor, and I'm trying to lower the current. If I'm trying to lower the current, we look at the rate of change. Again, if I'm trying to lower the current instantaneously at like 1 milliseconds, it's going to be a very big number, but it's going to be negative. If you think of rise over run, right, our slope is negative, or our slope is going down, so it's negative. Okay. So if we are trying to lower the current, we're going to have a negative rate of return, a rate of change, and so our voltage will be negative. We just talked about in the previous slide. It's negative because we got the charge again built up on the bottom side of the circuit. The mathematics follows where this will be a negative voltage, right? Because we're releasing energy into the system. Okay. Lastly, what happens if IUT constant? If the current never changes, well, the rate of change is zero because there is no rate. The rate's zero, nothing changes, right? So d over dt is equal to zero, which means we have no voltage, which checks out what we were talking about before. If the current never changes, we never have to take energy or dissipate energy, so there's no voltage needed to make the energy change, so it's naturally going to be zero. Nothing's creating... Voltage will only happen on an inductor if there's a bottleneck that causes charge to build up. If the current never changes, the inductor is fully charged, there is no pressure between the inductor, there's no voltage differential, and the voltage is zero, which is pretty much what this di over dt says. So with this type of logic, hopefully it makes sense why di over dt is here. It represents all of this. Right? They didn't just come out they didn't just make it out of nowhere. It actually makes sense. But if you understand the physics behind it, the equation, hopefully, it makes a little more sense. You won't be confused every time you see this. Okay. Opposite to this, we can figure out how much current is flowing through an inductor given the voltage we put across an inductor. Okay, so it's kind of opposite of the first. Right here is I is equal to 1 over L integral 0 to t of the voltage we put across an inductor, plus any initial current that happened before we started. So let's break it down. So remember an inductor sitting in a circuit. If we apply a voltage across an inductor, it's going to start building up energy. We put voltage, it's going to start taking current, it's going to start building up energy. Okay? How strong the voltage is, if it's 5 volts, 10 volts, or 50 volts, is going to make a big play. The bigger the number, the bigger the current, obviously. High voltage, high current, low voltage, low current. The other big factor is how long do we put it on. Something should tell you, if I have an inductor and I put a 5-volt source on for 1 second, and then I do it again and I do it for 50 seconds, which one's going to have more current? Obviously, putting a voltage for 50 seconds will build up more current, right? So the amount of time that we hold the voltage across an inductor will always be increasing the current. Okay, so that's why we have to calculate how much time we put on it. Okay. The 1 divided by L, think of L kind of like the inverse of resistance, right? Here, the bigger the L, remember, is a very big tank of energy. So if I have a very big L, it would take a longer time to fill it up. So let's say I'm going for 50 seconds. I got a bunch of voltage going. If I have a small L, it's going to fill up very quickly, and I'm going to have a current very fast. It's going to spike up really quick because it's a small energy tank. I don't need a lot of time and voltage to fill up a small energy tank. Well, what if I have a very big inductor? L is huge. It's a huge, giant tank of energy. It's like a pool. So it'll take a lot of voltage and a lot of time to fill up this pool to create a sizable amount of current. So that's why we divide by L. Right? Big pool, we divide by big number. Small pool, we divide by small number. So then the voltage can work quicker to create more current, induce more current, right? So that's the relationship of why we divide by L and why we integrate and why we have this voltage. Okay. This dt right here, by the way, this is where I don't like math, but this dt just tells you that you should take the time, multiply it, and that's it. dt has no, it's just like a little operator. It's not a variable itself. Okay. So that's this part. Now, the question is, what is this initial condition? What is I0 negative? So remember we talked about filling up that tank. Without this right here, this first part, we assume the tank's empty. We're starting at 0. So let's say you're filling your gas in your car. If you have 0 gallons and it's empty, you know how much you need to fill up. Well, what if the tank's already half filled? Well, you need to take that into account when you're filling up your gas tank. You don't want to overflow it. Same thing here. What if the energy in the inductor was already there before we started? Let's say the inductor was 50% full, right? If we don't take that into account, then this number will be incorrect. So we need to make sure that if we have previous energy in the circuit, we have previous current flowing before we interacted with the inductor, is accounted for. You can't just throw this away. Okay, so figure out what your initial condition is before we start messing with the circuit right here and add that into the current. Okay, and this could be negative, by the way. It doesn't always have to be positive. For example, what happens if we have negative current flowing through and the inductor was actually pushing energy into the circuit and we want to reverse it? So let's say it was negative 10 amps and I want to turn it into positive 10 amps. So my net difference to make positive 10 amps or negative 10 amps is I need to put in 20 amps worth of current. So if I didn't put negative 10 here and I only put 10 here, then this number wouldn't have been correct, right? So that's why we need to see the initial condition. Lastly, what's the average power in an inductor? It's a simple. And at the end of the day, it's going to be 0 watts. Why? Because an inductor is just a storage device. It doesn't absorb energy. It doesn't create it. It just takes it in today and gives it back tomorrow. But at the end of the month, eventually the inductor will net at 0 energy because it can't destroy energy. It can't produce it. It just passes along from one point to another. It takes it in today, gives it out tomorrow. Okay? It's very important to note that at the end of the day, there's no power absorbed by an inductor. Okay? It's not a resistor. Temporarily, it could change stuff, but eventually it has to give the energy back. Okay? So that's inductors for you. We could do the same thing for a capacitor. I'm going to go a little bit faster because capacitor inductors are very similar. We'll do the same thought process. Okay? Capacitors always resist the change of voltage. Inductors resist change of current. Capacitors resist the change in voltage and tries to keep it steady as much as possible until it runs out of energy. Okay? Capacitor will always act like a sponge and absorb or supply energy to resist the change in voltage. Okay? And the capacitor will store its energy in an electric field. Inductors use magnetic fields. Capacitors use electric fields, if you remember from 161. Right? So this is a circuit where we're trying to charge a capacitor. So let's say we have a circuit that has a 10-volt source, and then we're going to connect it to a capacitor that has 0 volts. So this is empty. Okay? So remember, capacitor will always say, no, I don't want to go to 10 volts immediately. We need to slow down and go from 0, I'll go to 1 volt to 2 volts to 3, 4, 5, 6, 7. I will not go from 0 to 10 immediately. We're going to have to build it up slowly. Okay? Okay, how do we build up the voltage? We got to put current into the inductor. There's no energy here. We need to push energy and store it in the electric field to make the capacitor build up its voltage. Okay, so delta V, the voltage across the inductor starts at 0 volts, and then we're going to turn the circuit on. Current's going to flow, and eventually this voltage will get to 10 volts. It'll fill up. So at 10 volts, the capacitor is full of energy, and then we're back at steady state. So that's how we charge a capacitor. Is we put a high voltage on it, and we watch the current rush in. Okay, how fast does it come in? Well, that's based on the time constant, that RC time constant, all that stuff you learned from first order differentials from engineering 17. That dictates how fast this is. It really depends on how big the capacitor is. The bigger the capacitor, the longer it takes to rise up the voltage. Okay, but capacitors are very good if you want to keep the voltage steady. Okay, because once we're at 10 volts up here, the capacitor is going to keep the circuit at 10 volts. So let's say we want to, all of a sudden the source says, I need to go down to 5 volts. Okay, what is the capacitor going to say? Nope, we can't go immediately to 5 volts. I'm at 10 volts and I have a lot of energy. So I'm going to keep the circuit steady at 10 volts as much as I can. And I'm going to release energy from my electric field to keep the voltage as high as I can. So right when the source goes to 5, then the capacitor will start releasing energy and reversing the current. Notice that the current is going the opposite direction of the charging phase. Because the only way for the capacitor to release energy in the circuit is current has to flow out of it, obviously, right? So as current flows out, the capacitor will be charging the circuit. Capacitor will also be charging the source, and it'll go from 10 volts to 9 volts to 8, 7, 6. Eventually, it's going to steady out at 5 volts. But it's going to take time to release the energy to bleed it out and say, okay, now we go to 5. So you see, if the capacitor is at 10, it's not going to immediately go to 5. It's going to have to say, let's get some energy out, and we'll do a nice slow landing to 5 volts. And that's good because sometimes circuits, you don't want abrupt changes in voltage. You might burn things out. Okay, so that's pretty much how capacitors work. It's a giant sponge of energy that stores electric field, and it just dumps it out when it needs to, and absorbs it when it needs to. Okay, so kind of rehash of everything. If you have a capacitor and you're trying to increase the voltage of the capacitor, make it higher, the current is going to change, or the current will have to start flowing into the capacitor. So capacitor is going to see a positive current flowing into the capacitor to charge electric field. We're going to have to absorb a bunch of energy to charge that electric field. Okay. Now, once the capacitor is charged up with a high voltage, if I want to decrease the voltage, I'm going to have to let the current out. So the current's going to reverse polarity and it's going to be negative current, and we're going to release energy from electric field. And it's going to go back into the circuit. Okay. And lastly, as long as the voltage is steady, if we have a circuit and we get the capacitor up to 10 volts and we stay at 10 volts, nothing's going to change, right? The capacitor's happy, we're happy, voltage stays steady, no current's going to flow because we don't need to swap energy. Nothing changes. So 0 amps at constant voltage, this energy stays stored. There's no changing in energy, right? And capacitor is going to sit there and wait until it does change and then react. Okay, so at the end of the day, capacitors are a very good device to help keep the voltage steady when you need to. Okay. All right, so that's capacitors for you. Now let's talk about the equations. Very, very similar looking equations, kind of the opposite of an inductor, right? The energy stored in a capacitor is 1/2 C times V squared. Okay, C is farads. It's just a way to show how big the capacitor is. A very small C means it's a very small capacitor with a very small electric field capacity. You don't need a lot of energy to fill up a small capacitor. A giant capacitor the size of a 2-liter bottle, it's going to be like farad level. It's going to take a lot of energy to store it, to change it. Okay, so the amount of energy that a capacitor can store is directly related to how many farads it has. That's why you have a C right here. Okay. Other thing is how much energy is stored in a capacitor is based on your voltage. You put voltage across the capacitor, you're going to start charging the energy, and you're going to charge it at an exponential rate. That's why it's V squared. Okay. So this is how you calculate how much energy is stored in a capacitor. So figure out how much voltage there is applied, figure out the capacitance, and there's going to be an upper threshold number, right? This is a hard number, right? It's going to be like 10, 20, 50 watts, and the capacitor is full, and then it just sits there and waits. Okay. Can we figure out the voltage across the capacitor? Yes. Right? It's very similar to an inductor current. It's 1/C times the integral 0 to t of the current going into the capacitor plus any initial condition. Now, why is it 1/C? Remember, C is the size of the capacitor. A bigger C means it takes more current to charge up to a specific voltage. If I want this VC to be 10 volts and I have like 5 amps flowing through, if I have a giant C, it's going to take 5 amps longer to charge up to 10 volts. If I have a very tiny C, this 10 amps will be very quick to charge up to 10 volts. Okay, so that's why I divide by C. It's the big storage tank of energy we divide by means it takes a lot of time to fill it up. A very small tank of energy we divide by means it's very quick to fill up a little cup. Okay. In terms of current, there's only one way to fill up the capacitor. You got to start dumping current into the capacitor. Okay, the higher the current, the bigger the amps, the faster it's going to fill up. That's obvious. It's always going to, if you put 1 amp versus 50 amps is going to fill it up 50 times faster, right? The other thing is time. If we take 5 minutes to fill up a capacitor versus 5 seconds to fill up a capacitor, obviously, given the current is constant, 5 minutes means we're going to have a lot more energy stored, right? We're going to have a lot higher voltage. So the amount of time you put the current into capacitor is going to raise its voltage. You have to calculate how long you're doing it. Okay. Lastly, you got your initial condition, V out negative. So this is how much energy was in the capacitor before we started counting. Same logic with the gas tank is if it's empty, this is 0. If the capacitor is half full, or your fuel tank's half full, you need to take that into account. So let's say if I want this to be 10 volts and I'm already at 5 volts, then my inductor only needs to work for the other 5 volts. 5 plus 5 equals 10. Okay. If this is negative 10 volts, I want to get this a positive 10 volts, then my current needs to work 20 volts worth of voltage to eventually get 10 volts. That's why you need to keep track of this pre-condition or the pre-charging capacitor. Very, very important. Otherwise, your equations will never work out. Okay. In terms of the current in a capacitor is C times dV over dt. Very similar logic is if we take voltage and put it across a current or across a capacitor, current's going to flow, right? So if we try to increase the voltage, meaning we go from 5 to 10 volts, so we're going up in voltage, the rate of how fast we go up is first is going to be positive, right? And then it's going to be a bigger number. So if we try to spike the voltage from 5 to 10 in 1 millisecond, yeah, this would be a huge number. If we go from 5 to 10 over 5 minutes, this is going to be a very small number, but it will be positive. Okay, so that's why the current is positive. Whenever you try to increase the voltage on a capacitor, current needs to flow in, and that's why it's positive. Okay. Now, if we have a high voltage and we want to decrease to a lower voltage, what do we have to do? Current needs to come out the capacitor. So current going out the capacitor is negative. That's why I have a negative here. Okay, so the math works out. And lastly, if the voltage doesn't change across the capacitor, it stays steady at 10 volts, then the rate of change is 0, so we have no current, which checks out because no current because we're not increasing or decreasing the energy. Remember, current's always only going to flow in and out of capacitor when energy needs to come in or out. Okay. And of course, average power of a capacitor is going to be 0 watts because the capacitor doesn't do any work itself. It will take energy for a small amount of time, but eventually it has to give it back. If I go, let's raise up to 10 volts, I would take energy out of the circuit to go up to 10 volts of the capacitor. But eventually my circuit is going to turn off, go back to 0 volts. So I'm going to release the energy back into the circuit to go back to 0. So at the end of the day, when you go home at 5 p.m., you turn off the lights, the capacitor is going to give the energy back. So the net power or the net energy absorbed by the capacitor or the average power is always going to be 0 because it doesn't do any work. You can't destroy energy, you can't create energy, it just temporarily holds it for you. Okay. Whew. So that's capacitors and inductors for you. I hope we kind of demystified it a little bit because, you know, this is probably your senior year. You need to come out of electrical engineering college, understand what capacitors and inductors do. I'll tell you, in my work, I guarantee you 9% of people, if not maybe 1 or 2 other person, truly understand what capacitors and inductors are. Most people don't even know, don't even care. They just look the other way. If you fully understand how this works, you're going to look like a genius to a lot of people. Because most people don't understand how it works. Okay, so this is just my foray in trying to help you out. Study on your own. You know, this is something in terms of physics you're going to have to really look into if you want to get really deep into it. Okay, so let's go ahead and summarize everything we learned today. We learned a lot about power, energy, inductors, and capacitors, and all that good stuff. So how do we define energy or work done in a circuit? Energy is always equal to the integral of the time we look at, and then we add the instantaneous power over that time. You just integrate over. And instantaneous power is always volts times current. At the exact time we keep looking. Every milliseconds, we're going to look at that instantaneous power and current, and we're going to add that into our integral. At the end of our period, or however long we had the circuit on, we're going to have a total amount of joules that the circuit used, absorbed, or supplied, and a total amount of kilowatt hours. They're interchangeable units. Okay, joules are the SI unit, kilowatt hours is more for electrical engineers. Okay. With the total amount of energy done or work done, we can also calculate the average power. Average power P is always equal to the integral of the time we look at multiplied by instantaneous power divided by the total period itself. Or we could just take the work, because this whole integral right here, this is just the amount of energy used. Another way to say it is just power equals energy divided by the time. Okay. And this is always in watts, by the way. Okay. I don't know if I mentioned there, but watts is the SI unit for power. Okay. Now for inductors, we talked about extensively, inductors in a circuit will behave they will resist the change in current by either absorbing or releasing energy from the inductor's magnetic field. And the voltage will follow suit, will be positive or negative based on releasing or absorbing energy. Okay? The capacitor will always behave in the circuit will behave by resisting the change in voltage. Sorry, this definitely should be voltage. Okay? Voltage. Okay? So resist the change in voltage by absorbing and releasing energy from the capacitor's electric field. Okay? So that's all I have for today. Kind of review of power and energy and some engineering 17 topics. We'll come back next time and start talking about AC power and all that good stuff. Okay? So thanks for showing up. Hope everybody has a good rest of the week, and we'll catch you next time. So see you around.